Alright, so here we got a Newton's second law problem. We got a block with a mass of 4 kilograms and it's placed on a 40-degree incline. We're told that the coefficient of kinetic friction is going to be 0.75. And part A of this problem says to find the block's acceleration. Alright, because this is a Newton's second law problem, we're dealing with forces, we want to draw a free body diagram. I'm going to go ahead and just draw the free body diagram on the picture that I've already drawn. I erased the M. That is mass M. Don't forget it. Okay. So I'm going to draw my forces on that. So the one I always start with is my weight force. So that's just labeled Fg, the weight force. Going to have the normal force always perpendicular to the surface, as you know. And then we're going to have friction, right? Because we're talking about friction. We got the coefficient. We're given the coefficient of friction. If the block is sliding down the ramp, which I assume that's the direction it's sliding, the friction force is going to be opposing that motion, so it's going to be pointed back this way. Alright. So that's my friction force, and it's going to be kinetic because we're talking about a block that's moving. Alright. Let's go ahead and define our coordinate system now. I remember having the discussion where it kind of makes sense to have the positive x direction, the direction that the motion is going, right? The block is moving this way down the ramp. I'm going to go ahead and define that as my positive x direction. And then perpendicular to that and parallel, as you will see, to the normal force is the positive y direction. Okay, so we got positive x direction in the direction of motion. Now, with this coordinate system, notice how two of the force vectors are already lined up with that. Normal force, again, is in the y direction, and the friction force it's in the negative x direction, but it's still aligned with that axis. So, the gravitational force vector, or the weight force vector, that one isn't. That one isn't aligned, so we have to decompose it. And when I decompose it, I make the y direction right there, so that's going to be my weight force in the y direction. Now I could draw my x direction vector here, or I could draw it here. I'm going to go ahead and draw it here, but keep in mind that you could have drawn it here as well, and it makes no difference. So that will be the weight force in the x direction. You can move vectors around as long as you don't change their direction or their size, they're exactly the same. Okay, and if I'd done that properly, they would make a nice little rectangle, and this angle in that triangle would be congruent to this angle. In any kind of situation like this, those angles will be congruent. You can prove it geometrically if you want, but I'm telling you, they are equal. They are congruent. So, I've done some vector decomposition. I'm probably going to have to do some trig, so let's go ahead and do that. Let's go ahead and just say, let's say cosine theta. Cosine of that guy is going to be the adjacent side, which is the y component. The y component of the wave force, divided by the hypotenuse, which is the weight force itself. Excuse me. Solving for the y component, just multiplying both sides by the wave force, I'm going to get the y component of the wave force is going to be the weight force times the cosine of the angle. And similarly, sine of the angle is going to be the opposite, which is this, which again is the same as the x component, the same size. So that's going to be the x component over the weight force. And if we multiply both sides by the weight force, we get the x component of the weight force is going to be the weight force times the sine of the angle. Now that's just prep work right now. We're going to have to use those in the future. Anytime you do a decomposition like this, you're pretty much going to have to do that. So I'm just doing that to get ready. Alright. We still need to find the block's acceleration though. And so we're probably going to have to do the whole sum of forces in the x direction and sum of forces in the y direction. So let's just go ahead and do that. Now, you might want to be thinking, we are going to have acceleration here. We're told that the block's going to be accelerating down this way. So if we sum the forces in the x direction, they're not going to add to zero, right? There's going to be a non-zero acceleration, so those forces aren't going to add to zero. We aren't going to be having any acceleration in the y direction, so those will add to zero. So I'm probably going to handle those forces first because they're going to be a little easier and they might help me with the x direction forces. So you're going to have to do both of them regardless. So it doesn't matter. I mean, you can do the x direction forces first, but because the y direction forces are a little easier, I'm going to handle them first. So if I take the sum of all the forces in the y direction, in the positive direction I have the normal force. And in the negative direction, so I subtract, I have the y component of the weight force. Now, because there is no acceleration in the y direction, the net force is 0, so the sum of all the forces is 0. Here we have an expression, right? We know that the normal force now is equal to the force of gravity in the y direction, if I add that to both sides. Okay. And I can actually expand that a little bit because we know that the normal force we know that the the y component of the weight force, as we showed up here, is just going to be the weight force times the cosine of theta. So we can make that substitution. We now know that the normal force is the weight force times the cosine of theta. Notice that hasn't found any acceleration, right? We don't know if it's going to be accelerating or not, but we now know the normal force in terms of things we can calculate. That might help us in the future. Okay, so let's go ahead and do the sum of forces in the x direction now. So my sum of forces in the x direction. And if we look at our free body diagram, in the positive x direction, we have the x component of the weight force, and in the negative x direction, we have the force of friction. Okay. Now those, because they are not in equilibrium, right? We have acceleration here. The sum of forces does not equal 0. The sum of forces by Newton's second law equals the object's mass times acceleration. And that's what we're actually trying to find. So to solve for acceleration, we just divide both sides by m, and we would get the x component of the gravitational force minus the friction force over m. So that's an expression for acceleration. We're going to have to plug in values for all those, though. And do we have all that? Well, do we have force of gravity in the x direction? Yeah, it's right up here. We can plug that in. The force of friction, isn't the force of friction equal to the coefficient of friction times the normal force? We are given the coefficient of friction up there. We know the normal force here, so we can make that substitution. So let's do that. So instead of writing the x component of the gravitational force, we'll go ahead and write this, because we have numbers for those. So that's going to be the force of gravity times sine theta, minus the friction force, which we're, instead of writing that way, we're going to write this way. We're just making this substitution over the mass of the object. Okay? We're getting there. Now the normal force, we have an expression for over here. So we can substitute that in. And the gravitational force, as we all probably know right now, is going to be mg, right? So anytime you see Fg, just like right here, you can write mg. So the normal force, another way of expressing it following from here, is mg cosine theta. So we can substitute that in. So doing that, we now have, instead of Fg, we're going to write mg sine theta minus the coefficient of kinetic friction times the normal force, but the normal force is mg cosine theta. And all that's going to be divided by m. Now notice something interesting happens. If you had made numerical substitutions before this point, you wouldn't see this. But because I'm doing everything symbolically, that m and that m get divided out because of that one. And so the acceleration is simply going to be g times sine theta minus the coefficient of friction times g cosine theta. Okay. And so working that out, we are going to have 9.81 times sine of 40. We are 40 degrees, yes. Minus the coefficient of kinetic friction is 0.75 times g, which is 9.81, times cosine theta, cosine 40. And when you work all that out, you get, let me do it in my head right now real quick, you get about 0.67 meters per second squared. Sorry, I should have kept my units in here, but I forgot. I'm kind of losing my voice here, so. You guys, I'm sure, will keep your units. 9.81 meters per second squared. Yeah, you get it. All right. So this is the acceleration that object, this crate, or this block would have in this situation. It would accelerate down the ramp at 0.67 meters per second squared. I hope you enjoyed that. We're going to revisit this problem, dig a little deeper into it in the next video.